Section 2.4, Dividing Polynomials, Remainder and Factor Theorems. So our objectives for this section is to use long division to divide polynomials, use synthetic division to divide polynomials, evaluate a polynomial using the remainder theorem, and then finally to use the factor theorem to solve a polynomial equation. So previously in 2.3, we were factoring polynomials in order to find their zeros and talk about a lot of different things that were going on with the polynomials, like end behavior, turning points, things like that. Not every polynomial is going to be able to factor perfectly, right? We were using mostly quadratic techniques and factoring with grouping a little bit in the previous section, but not every polynomial is going to work like that. Okay? So we need some other methods to be able to factor them effectively. So in order to factor polynomials, we are going to divide out factors that work, and we're going to simplify the resulting polynomial. So in order to do that, we need to know how long division and synthetic division works for polynomials. Then we can make the resulting polynomial simpler and be able to factor it with some of the techniques that we know already. All right, so before we do this, let's look at the long division algorithm. How does long division actually work? So we're going to go way, way, way back to whenever you first saw this in 5th grade, 3rd grade, whatever. Okay, so let's remember how long division works step by step, and then we'll take the same steps and use them with polynomials. Okay, so the first thing I do is I look at this first term right there. Can I divide what's outside into 1? No. So I look at the next two terms, and I say, does 11 go into 18? Yeah, it goes one time with some left over, and I write that 1 up on the top. Then I take what's on the top and I multiply it by the 11. So 1 times 11 is 11. Then I subtract. So 18 minus 11 is 7. Then I bring down the next term and start all over again. Does 11 go into 77? Yeah, 7 times. Multiply 77, and we get an answer. Subtract, and we get an answer of 0. So that means that 11 times 17 is going to be equal to 187, right? Because that's what we're doing. We're taking a factor of 17 out of the, or sorry, we're taking a factor of 11 out of the 187, and we're left with 17. Pretty simple. Our algorithm is look at my quotient here, figure out what goes into it, multiply, subtract, do it again. Okay? So let's do this now with polynomials. So long division of polynomials and the division algorithm. So we can begin by looking at division by a polynomial containing more than one term, like this. The divisor has 2 terms, it's binomial. The polynomial has 3 terms, and it's trinomial. So we're going to divide a trinomial by a binomial. And you're probably thinking, well, this one's pretty easy because it actually factors. Yeah, it does, but it's not going to happen all the time, number 1, and you're not going to be able to notice it all the time, number 2. So let's get an idea of how this actually works, and then we can use it for any problem. So when a divisor has more than one term, the 4 steps used to divide the whole numbers, divide, multiply, subtract, bring down, form the repetitive procedure for a polynomial. Just like we did here. We divided, multiplied, subtract, bring down. Okay? So let's do it. So we're going to go x plus 3, and we're going to divide x squared plus 10x plus 21. Okay? So we're going to use the same steps. Divide. Okay? So first of all, I arrange these. And second, how many times? Now we're going to focus on just the first term. The plus 3 sort of like goes along for the ride right here. Okay? So we focus on the first term and the first term here. How many times does x squared, or so how many times does x go into x squared? what times x gives you x squared? And the answer is x. So we're going to write x squared over x is x. So we're going to write this as my first term, but I'm going to line it up. So I don't put it over the x squared because they don't match. I put it right here. So the powers match. Okay, and this is just a way to keep things organized for ourselves. Okay, so that's divide. Now I'm going to multiply. Okay, so I take the x and I'm going to multiply it by x plus 3, okay, which gives me x squared plus 3x. Okay, next, subtract. Okay, so we're going to subtract, and the way I like to do this is I like to change the signs of both terms. These two cancel, which was the point. If it doesn't cancel, we have a problem. 10x minus 3x gives me 7x plus 21. Bring down the last term. Okay, divide, multiply, subtract, bring down. Okay, do it all again. How many times does x go into 7x? So we're looking at 7x over x is 7. That's divide. Multiply. 7 times x plus 3 is 7x plus 21. Subtract gives me 0. And there's nothing left to bring down. So what does that mean? It means that the quotient of this expression is x plus 7. The remainder is 0, so we can conclude that the two factors of this trinomial, x squared plus 10x plus 21, are x plus 3 times x plus 7. Okay, and we could think of this as x squared plus 10x plus 21 over x plus 3 is going to equal x plus 7. Okay, which we should have kind of known already, since this term, this thing up at the top actually factors into x plus 3, x plus 7 over x plus 3, which would then cancel those two out. But again, not everything we're going to look at using these methods is going to factor. It's just nice to start with an easy problem that does. Let's try one more. Okay, so we're going to go x plus 9, x squared plus 14x plus 45. Divide, multiply, subtract, bring down. Okay, so divide. That's x, because x squared divided by x is x. X plus 9, multiply, subtract, x squared, 9x, sorry, subtract, we get 5x, bring down, 45, divide 5x by x, that's a 5, and 5x plus 45, when we multiply by 9, subtract, and we get a remainder of 0. Which again means that x squared plus 14x plus 45 divided by x plus 9 is x plus 5. And we could also say that x plus 9 times x plus 5 is x squared plus 14x plus 45. Okay. Before looking at additional examples, let's summarize the general procedure for dividing polynomials before it gets more complicated. Okay. So my procedure for long division is, number 1, arrange the terms of both the dividend and the divisor in descending powers of any variable. That's important. Always write them in the correct order. Always write them in standard form. Divide the first term in the dividend by the first term in the divisor. The result is the first term of the quotient. Okay, that's what we did right here. We took this, divide by this. The answer is my first term in the quotient. Okay. Next, multiply. Multiply every term in the divisor by the first term in the quotient. Write the resulting product beneath the dividend with the like terms lined up. That's important too. Line up the like terms so you can stop from making a mistake. Subtract the product from the dividend, bring down the next term in the original dividend, and write it next to the remainder to form a new dividend. Use this new expression in the dividend and repeat this process until the remainder can no longer be divided. This will occur when the degree of the remainder, the highest exponent, is less than the degree of the divisor. So as soon as the degree here becomes less than the degree up here, we're done. Okay, so we haven't seen that yet, but be aware. Okay, divide, multiply, subtract, bring down. This method will work for any polynomial division problem that we have. Now, we're going to see an easier method in a few minutes that will work for specific types of polynomial equations. Okay, but for now, let's look at one that's slightly harder. Okay, so step one, rearrange this and write it out. So we have 3x minus 2, and we're going to divide into, we don't write my equation like that. It's not in standard form. So we change it to 6x to the third minus x squared, make sure my signs are correct, minus 5x plus 4. Now I can start my long division. And I start by dividing, and just looking at this polynomial right here, I have no idea how it factors. Okay, I could maybe attempt grouping, and it won't work. Okay, so I have really no idea how this is going to work out. So I'm going to have to do long division. So my first step is to divide 6x to the third power by 3x, which gives me 2x squared. And I'm going to write that, just for organization purposes, over the term that has x squared in it. Multiply. That gives me 6x to the third power minus 4x squared. Okay. Subtract. So I'm going to change the sign of everything. So this changes into a negative 6. This changes into a positive 4. Okay. Those two cancel. And I'm left with 3x squared. Bring down the minus 5x. Okay. I'm not going to bring down the 4 yet. Okay. I'm only going to bring down the first term. Okay. Now I do this whole problem over again. Divide. 3x squared by 3x is just x. Multiply. 3x squared plus 2x, right? I multiply the x times the 3x plus 2. Subtract. Okay, so that cancels, which is good. Minus 7x. Little mistake here. Positive x times negative 2 is a minus 2. Then when I subtract, it changes to a positive. And we get a minus 3x. Sorry about that. Bring down the 4. And do it all again. So now, when I divide, negative 3x divided by 3x is minus 1. Okay, which gives me negative 3x. Minus 1 times minus 2 is plus 2. Subtract, and I get 2. Now, okay, sometimes when we were dealing with long division back in the day, we put a decimal and we kept going. We're not going to do that with polynomials. We're just going to leave this as the remainder. Okay, so now we can see that these two, that this polynomial is not divisible by this, not evenly anyway. Okay, so my answer becomes that plus a remainder. Okay, the way we're going to write this is we're going to write my answer as 2x squared plus x minus 1, not that. I don't know who learned how to do remainders like that, but we don't just put a remainder 2. But we are going to write this as a fraction. So we're going to add 2 over the divisor, which is 3x minus 2. Okay? So this is what 6x to the third minus x squared minus 5x plus 4 divided by 3x minus 2 is actually equal to. Then if I clear the fractions on both by multiplying both sides of this statement, which is true, this equation is true, if I multiply both sides by 3x minus 2, I would get that 6x to the third minus x squared minus 5x plus 4, my original polynomial, is equal to 2x squared plus x minus 1 times 3x minus 2 plus a 2 left over, plus a remainder of 2. Okay? If I had multiplied both sides of the equation by 3x minus 2. Okay? So what that says is that my polynomial right here is equal to my answer times my divisor, my quotient times my divisor, plus the leftover remainder. Okay? And that illustrates the division algorithm. We'll look at that in a second. Let's do another problem. Okay? So we're going to go with x minus 3. And we're going to divide 2x to the third minus 3x squared minus 11x plus 7 by x minus 3. Everybody, make sure you realize how I rewrote this in standard form. Biggest exponent to smallest exponent. Okay, divide, multiply, subtract, bring down. We're going to divide 2x to the third by x, which gives me 2x squared, which gives me 2x to the third when I multiply, and a minus 6x squared. Subtract gives me 3x squared. Bring down the minus 11x. Do it all again. 3x squared divided by x is 3x. 3x squared, when I multiply 3x times the x, 3x times minus 3 is minus 9x. Subtract gives me a negative 2x. Bring down the 7. Divide, minus 2, minus 2x plus 6. And subtract, change both signs, and we get 1 left over. So my answer becomes 2x squared plus 3x minus 2 plus 1 over x minus 3. That's my remainder. That's what's left over, and 1 is no longer divisible by x minus 3. Okay, so we talked about this before, that the divisor times the quotient plus the remainder is going to be my dividend, my original problem, just like we had in this first problem right up here. Okay? And this is how you would check. If you want to check your answer, you could distribute these together, just add 2 to the constant term, and you should get your original equation. Okay, so this is the division algorithm. That the dividend, so let's look at this whole thing. That f of x and d of x are polynomials with d of x not equal to 0. The degree of d of x is less than or equal to the degree of f of x. Then there exist unique polynomials q and r such that the dividend is equal to the divisor times the quotient plus the remainder. And this remainder doesn't just have to be a number, it could also be some sort of function of x. If it is 0, if the remainder is 0, or if the degree is less than the degree of d of x, right, then we can say it divides evenly into f of x, and that d and q, this and this, are factors of that. Okay? And that's true if there is no remainder, if the remainder is equal to 0. Okay? Now, I said there was an easier way to do this, because obviously, if you look at these can take a little while. So, before we get to the easier one more problem. Okay? If a power of x is missing in either the dividend or the divisor, add that power of x with a coefficient of 0, then divide. In this way, like terms will be aligned as you carry out the long division. So, that means that if we have this, as I'm looking at this expression, I notice a couple things. X to the fourth, x to the third. There is no x squared. There is no constant term. Okay, so when we do this, in order to keep everything aligned, you should put missing zeros into the problem. Now, we don't really have to put it on the end of the divisor, but we definitely must put it in the middle here. So let's do this 3x squared minus 2x, 6x to the fourth, plus 5x to the third, plus 0x squared, plus 3x minus 5. Okay? By including this term, by including the 0x squared, we will keep everything aligned. We will make sure that we don't make a mistake, and we will count, and you'll see why we actually need it. Okay, so the steps are going to be the same. The only thing that's different is our setup here. So divide, multiply, subtract, bring down. Divide, we are going to get 6x to the fourth, and I'm going to divide it by 3x squared. And clearly, that is going to be 2x squared. Okay, so my first term is 2x squared, but I always want to put my first term over the one with the same power of it. So if I didn't put this in here, I would have nowhere to put the 2x squared, number one, which I want to put it there. And number two, watch what happens in our next term. Multiply 6x to the fourth minus 10x to the third. Sorry, I was looking at the 5. 6, 2 times 3, minus 4x to the third. That's it. Subtract, and we get 9x to the third. Bring down the 0x squared, okay? Because now that helps you keep this next term organized, and then when I divide and get 3x, multiply, we now get 9x to the third minus 6x squared. If I didn't put that 0x in there, there would be nothing for me to add the 6x squared to. Bring down the 3x and divide 3x squared by 6x squared, we get 2. Well, hold on a second. I reached the end up here. Watch what happens. 6x squared minus 4x, subtract, and we get 7x, bring down the minus 5. Now notice that the degree of my remainder is 1. The degree of my divisor is 2. The degree of the remainder is less than the degree of the divisor. We're done. And 7x is not divisible by 3x squared. There's nothing that you can multiply 3x squared to give you 7x, right? The degree is too small, which means my answer becomes 2x squared plus 3x plus 2 plus the remainder divided by the divisor. So that's 7x minus 5 over 3x squared minus 2x. And that's as simplified as it gets. Let's try another one of those. Okay, so we're going to do x squared minus 2x, and we're going to divide that into 2x to the fourth plus 3x to the third. Make sure you put the x squared minus 7x minus 10. Okay. Divide, multiply, subtract, bring down. Okay, so divide. We're going to get 2x squared. 2x squared times x squared is 2x to the fourth. 2x squared times minus 2x is minus 4x to the third. Subtract, we get 7x to the third plus 0x squared. When I bring that down, that's going to be a plus 7x, which gives me 7x to the third minus 14x squared. Subtract, minus 7x. When I bring down the minus 7x, I'm going to have to multiply 14. So that's 14x squared. That's going to be a minus 28x. Subtract, and I get 21x minus 10. We're done because the degree of the remainder is less than the degree of the divisor. Okay, so my answer becomes 2x squared plus 7x plus 14 plus 21x minus 10 over x squared minus 2x. We can also say that my original expression, 2x to the fourth plus 3x to the third, I don't need to put the 0 here, minus 7x minus 10 is equal to x squared minus 2x times 2x squared plus 7x plus 14 plus the remainder. Okay? So we can still use that part of the division algorithm to say that the divisor times the quotient plus the remainder is equal to my original expression. Okay? Now let's get to the easier method. Okay, so synthetic division is a nice little trick that we can use to divide polynomials if it's of the form x minus c. So just an x, not an x squared, with no number in the front, plus or minus some number. Okay, if it looks like this, we can divide things very quickly. Okay? So let's compare the two methods showing you how we can divide this cubic polynomial by a binomial with a 1 in the front. So long division, we see that we have my divisor, we have my dividend, we use our little algorithm, right? Multiply, divide, multiply, subtract, bring down, divide, multiply, divide, multiply, subtract, bring down, bring down, bring down to get my remainder. Look how long this is. Okay, we can break this down with a nice smaller little thing called synthetic division. Okay, so my divisor is x minus 3, which means that c is equal to 3, which means if I set this equal to 0, x is equal to 3. That's what goes right there. Okay. Next, when we look at this, right, notice that the coefficients of the polynomial go 1, 4, -5, +5. The divisor, right, we already said is going to be 3. And then this happens to be the coefficients of the quotient. Look, 1, 7, 16. 1, 7, 16. 1, 4, 5, -5, 5. 1, 4, -5, 5. Okay, these numbers don't really matter. They just help you to get the answer. And notice where they occur. 3, 21, 48. Okay. So we don't really need those. We just need them to get the answer. The important ones are what we put here, what we put up top, and of course my answer, and the last term, which happens to be my remainder. And sometimes when I'm doing this, I like to put a little bar right there off the last one to remind me that that last term is a remainder. Okay, so you can do that, or you don't have to. Okay, so let's look at the steps that we are going to use to use synthetic division. Step 1, arrange the polynomial in descending powers. That doesn't change. Now this is even more important, to have a 0 for any missing terms. Okay, write C for the divisor x minus 3, which basically means you just change the sign. So we're looking for the root, not the factor, right? We want to know what x is equal to. So for x minus 3, x is equal to 3 in that case. First step is always write the leading coefficient of the dividend in the bottom row. So you first bring down the 1, always, or whatever number it happens to be in the front. Okay, you draw this line right there, and you bring down the first number. Next, we multiply. So we take 3 times 1, and gives me 3, and I write the answer in the second column. Okay? Multiply C times the value just written on the bottom row, write the product in the next column in the second row. Now, the nice thing about synthetic division is that you are adding instead of subtracting, which is kind of why we changed the sign of that term right there. Okay, so with long division, it's easy to make a mistake with signs because you're subtracting. With synthetic division, it's nice because all you have to do is add. So you add straight down, we get this 7, and then repeat. And then so we multiply the 3 times the 7, gives me 21, and I put it up and to the right. Add, multiply, again, add, and then finally, we use the numbers in the last row to write the quotient plus the remainder above the divisor. The degree of the first term, this is important, the degree, that's why it's in bold, the degree of the first term of the quotient is always 1 less than the degree of the first term of the dividend. So we started with x to the third, my answer is going to be x squared because we're dividing out a linear factor. We're dividing out an x minus or plus some number. So when we divide an x to the third by an x, we're going to get an x squared. Let's see how this works. Okay, so I'm going to use synthetic division to divide 5x to the third plus 6x plus 8 by x minus 2. The biggest mistake you can make in this problem is in the setup. Okay, so first we see that x is equal to negative 2 when we set that equal to 0, because it's always x minus c. In this case, it's x minus negative 2. Okay, so we take negative 2, we put it in our little box. Then we take the coefficients here. But if I do that, I'm going to get this wrong, okay? Because you must include any missing zeros, especially when you're using synthetic division. You have to make sure you include the missing zeros. So we have 5x to the third. We're going to have a 0x squared. We're going to have a 6x. We're going to have an 8. Draw a line. Leave some space, okay? That's your setup. That's my setup for synthetic division, okay? First step, bring down the 5. Next step, multiply. Negative 2 times 5 is negative 10. Add. 0 plus negative 10 is negative 10. Multiply. We now get negative 2 times negative 10 is positive 20. Add them together, you get 26. Then multiply negative 2 times 26 is negative 52. Add negative 44. When you get to the end, you're done. Okay? So look at your answer here. And we start with 1 degree less. So this becomes, this becomes 5x squared minus 10x plus 26 minus a remainder 44 over x plus 2, because that's what I divided by. Okay, not over negative 2, okay, but over x plus 2. And that also tells me, because there was a remainder, that x plus 2 is not a factor of 5x to the third plus 6x plus 8. Okay? And that is something that we'll use a little bit more later. Let's try again. Let's use synthetic division. And you can see how much quicker this is than long division. Okay, so I start with negative 2. I put it in my little box. I go 1, 0, 7, negative 7, negative 6. Draw a line. Bring down the 1. Multiply. Add. Multiply. Add. Multiply. Add. And we get a 0. You know, notice I put this little line here that just helps me remember that the last term is the remainder, and this actually tells me that x plus 2 is a factor of x to the third minus 7x plus 6 because the remainder was 0. And the answer is x squared minus 2x minus 3. Okay, and now you might even notice that my answer is now something that I can factor using quadratic techniques into x minus 3x plus 1. So that's sort of where we're heading with this, in that we can use the synthetic division techniques to simplify this expression, which was an x to the third power, which I don't know how to factor, which I can't factor using conventional methods, bring it down, reduce it to something that can factor with quadratic techniques, and now I can factor and find all of the roots of this particular expression. Okay? And that's where we're going to go next section. Okay, so the remainder theorem. So let's consider the division algorithm when the dividend f of x is divided by x minus c. In this case, the remainder must be a constant because its degree is less than 1. Okay? So when I multiply the divisor times some sort of quotient plus the remainder, it is going to be a constant because the degree has to be less than x, or else I could keep dividing. This means that if I were to plug in c, if I wanted to find f of c, right? When I plug in c, I would get c minus c would be 0 times q of c. Who cares what that is? Because 0 times anything is going to be 0. So the answer is going to be the remainder. So what does that mean? It means that if a polynomial is divided by x minus c, the remainder is the value of the polynomial at c. And that is the remainder theorem, which says that if a polynomial f of x is divided by x minus c, the remainder is f of c. And our next example, example 5, shows how we can use the remainder theorem to evaluate a polynomial function at 2. You could, of course, do the longer method of plugging into the function, evaluating everything at 2. But if the numbers get a little bit bigger and maybe you don't have a calculator, it might be tough to cube or raise something to the 4th power, this is another method to evaluate a function at a specific point. Okay? So rather than substituting 2 for x, we divide the function by x minus 2, and the remainder is f of 2. So use the remainder theorem to find f of 2, which means we're going to divide by x minus 2. Okay, that's important because when we use the synthetic division, we change the sign. We use the remainder theorem when we are evaluating f of 2, we're just going to put 2 in our little box up here. Make sure there's no zeros that I need to put in. So that's 1, minus 4, 5, and 3 as I strip the coefficients. Break down the 1, multiply, add, multiply, add, multiply, add. My answer is 5. Okay? So if I want to evaluate this function at 2, again, I could do 2 to the third minus 4 times 2 squared minus 5 times 2 plus 3. Okay? But I'm going to get the same thing. I'm going to get 5. Let's try again. Use the remainder theorem to find f of negative 4. Negative 4 goes in my little box. We have 3, 4, minus 5, 3. Line, bring down the 3. Multiply, that's negative 12. Add, that is a negative 8. Multiply, that's a minus 32. Add, we get a minus 37. Multiply, we get 148. And add, we get 151. So much easier to do this than to cube this, to cube negative 4, add it to 4 squared, 4x squared, and work it out the longer way. Okay. Next is something called the factor theorem. So let's look again at the division algorithm when the divisor is of the form x minus c. Okay, so we've seen this a couple times already. My dividend equals the divisor times the quotient plus the remainder. By the remainder theorem, the remainder r is f of c. So I can replace this r with f of c. And if f of c is equal to 0, then the function just equals the divisor times the quotient. Okay? So x minus c is a factor of f of x, which means that for the polynomial function f of x, if f of c is equal to 0, then x minus c is a factor. So if we reverse this and see what happens if x minus c is a factor of f of x, this means that f of x is equal to x minus c times q of x. And if we replace f and f of x with c, we get that that is equal to 0, and f of c is equal to 0, and we have proved the factor theorem is actually true. So what does the factor theorem actually say? It says that if f of c is equal to 0, then x minus c is a factor, which means that we can use this theorem, we can use this idea to factor and solve polynomial equations, like this one. If you know that 3 is a 0 of the function, that means f of 3 is equal to 0. That means that x minus 3 is a factor. That means that I can factor out, right? This is what I was talking about before. We can factor out the x minus 3 using synthetic division, and then because the degree is going to go down by 1, I can then use quadratic techniques to factor the rest. Let's see what happens. So 3 is a 0. So we have 2 minus 3 minus 11 and 6 with synthetic division. Okay, I could try to use long division, but it would take much, much longer, which is why it's called long division. Bring down the 2, multiply, add, multiply, add, multiply, add, and it is a 0. That's nice that they didn't lie to us. Okay, so the resulting equation is 2x squared plus 3x minus 2, which I can then, well, first of all, let me get the whole polynomial factor. Okay, so my first factor, right, this is my first factor, but it's not a 3. Remember, it is x minus 3. And then here's the rest, 2x squared plus 3x minus 2. Okay, I have to see if this factors, so I'm going to use the factor method, right? The factors of 1 and 2 times the factors of 1 and 2. That subtract and give me 3. When I make my expression, right, that's 2x and x. When I plug these in, I get minus 1 and a plus 2. Inside pair is negative 1, outside pair is positive 4. Subtracting those give me 3. Good. So this factors into x minus 3 times 2x minus 1 times x plus 2, which makes my 3 answers, right? Because we want to solve the equation. So x is going to be equal to my solution set. Nice to put them in order if you can. This one, negative 2. This one, 1/2. This one, positive 3. Those are the 3 zeros of the polynomial function, which means that the graph is going to cross the x-axis at these 3 points. And then I can also use what I learned last time, is that the leading coefficient is 2 and the function has a odd exponent, which means it's going to fall to the left, rise to the right. I could, I know that the graph is going to go straight through the x-axis at those 3 points because none of them repeat. And I could plug in a few more points in order to get the graph. Okay, so that's sort of putting everything together. What we'll do next section is we'll see that that will not be given, and we'll figure out how to find the zeros that could work for this polynomial equation. For now, let's just try one last problem. So given that given that negative 1 is a 0, right? We can go like this. we can say 15, 14, minus 3, minus 2. Double check that I don't need any zeros. I don't. Bring down the 15, multiply, add, multiply, add, and multiply. And if you didn't get 0, you probably should check your work because I don't think the question is going to lie to you. Right? So it's given that -1 is a 0. The reason why we actually did this is to get my resulting equation, 15x squared minus x minus 2. Now, I can factor this. Factors of 15, 5, and 3. Factors of 2. How to get them to subtract to -1. We're going to get 5x, 3x there. And we want the 5 multiplied with the 1, the 3, and the 2 to give me a -6 and a +5. So my factored answer is going to be, that's my first factor. Don't forget about that one. It's x plus 1, always the opposite, right? Because given that -1 is a 0, that means x is equal to -1, which means if I set it equal to 0 to get the factor, we have that x plus 1 as my factor. 5x minus 2 and 3x plus 1, which makes x equal to, let's try to put these in order, -1, -1/3, and +2/5. Ooh, ugly brackets, but hopefully you get the idea. That was the factor theorem. So based on the factor theorem, the following statements are useful in solving polynomial equations. 1. If f of x is divided by x minus c and the remainder is 0, then c is a 0 and c is a root of the polynomial equation f of x is equal to 0. If it's divided by x minus c and the remainder is 0, then x minus c is also a factor. So all of these things are what happens is when you have these things, when you have the function equal to 0, right? It's a 0, it's a root, and if you move the number to the other side, right, you can actually have a factor, right? If f of 3 is equal to 0, that means that's a 0 of the function. That means that's a root of the function, and it means that x minus 3 is a factor of the function. Okay, and that was 2.4, dividing polynomials, the remainder, and factor theorems. So do Math Excel 2.4.